south of Fall City. My brothers and I farm down there, about 4,000 acres. Well, about a third of that is irrigated. So most of our production is dry land. We have pivots and drip irrigation on our farm. We have about 1,500 acres total irrigated. About 500 acres of that is subsurface drip. So NutriDrip is our primary business. This is our team that we have, that we go out and we install and maintain drip irrigation systems. And because we're in the drip irrigation business, it has led us to focus on water quality, because water quality is so important when we're talking about a drip irrigation system. If it's not properly maintained, it's going to plug up. And we've learned a lot of things in our drip system that now we apply to our center pivots. So I think hopefully we'll share some information that applies no matter how you irrigate. So what does NutriDrip do? We design, install, and maintain drip systems. We do a lot of moisture probes, fertigation, agronomy work, and manure separation. So I'm going to spend most of my time just talking about the water quality piece of this. So kind of where our journey started in this is a yield map for back in 2020. One of the fields that we have a center pivot on, it's a windshield wiper that sits here. And if you notice this corner right here, the corner out-yielded the irrigated portion of the field by 21 bushel. And we started asking questions why. Why would a dryland corner, now it was a year that we had ideal rainfall, okay? So a year where it rained perfect, I think we only irrigated 2 inches, and that was just to get some fertilizer out. But still, why would we have a situation where we have a significantly better yield in a dryland corner? So we started digging into that. And this is another picture from one of our customers out by Holdridge, Nebraska. Kind of the same thing. You can see that underneath that pivot, much better plant health outside the pivot than inside the pivot. And so why, we started asking questions, and we get asked this question frequently, where farmers are saying, I'm putting water out, but I don't feel like I'm getting the response I should. Or I'm fertigating, and that fertigation isn't working the way that it used to. So what we dug into is, first of all, we looked at the soil, and we said, what's going on? We took soil samples both from inside the irrigated area and outside the irrigated area. And over here on the left-hand side is a standard soil test. And if you notice, I've highlighted the calcium numbers, and they're the same. So the calcium levels inside and outside the pivot are identical. If we move to the plant available calcium, so this is an H3A or a Haney extract, over here on the right-hand side, this got cut off. We're at 433 here on the corner, and this one down here is 30% less. So underneath the pivot, my standard soil test says I'm the same calcium levels under the pivot and outside the pivot, but for some reason the plant available calcium is not available underneath the center pivot. And to go a step further, my water is high in calcium. This particular irrigation system is coming off of a reservoir, and our natural runoff there has a lot of calcium in it. And so we would traditionally say, well, our calcium should actually be higher where we've been irrigating. So we dug into this a little bit further and started to understand what are these water samples telling us, and understanding what good water looks like versus bad water. And so on the right-hand side here, I've got what I would consider a very good water. Over here on the left-hand side, something that's not so good. So I'm going to point out just a few things here to kind of pay attention to when you look at a water sample. And a water sample is always that's always the first piece that we want to look at, is what's in that water. And I'll share a little bit more about that here in a minute. So the first number we look at is electroconductivity. Electroconductivity is the amount of total salts in the water. If we had distilled water or reverse osmosis water, this electroconductivity would be 0. If we put a electrode in this side and we stuck our finger over here, it wouldn't shock us. That water would not conduct electricity. This water has a 0.26, so you would get a tingle if you stuck your finger in on this side. If you go to this water here, has an electroconductivity of a 2.4, you get a pretty good shock. That water is going to conduct a lot of electricity because it has a lot of salts in it. Now, when I first got into this, and I'm not a chemist, I'm a farmer, when I heard the word salt, I automatically thought of what I use at the table. Salt is a general term for all kinds of chemicals. So all of these different elements here are different kinds of salt. Sodium is a salt, potassium is a salt, calcium, magnesium, nitrate, sulfate, all of these are different salts. This number here is an accumulation of those salts. So it's the first number we want to look at on a water sample because it tells us, do I have a problem here, or is this water empty, or is it blank? If I'm an irrigator, I would rather have water that is fairly empty. I don't want much in it because all of these things that are in this water are going to cause antagonisms. And this starts to get into chemistry and cations and anions, and we could spend several hours talking about cations and anion balance and what it's doing in the water. But a couple things I want to point out in particular here. The number one antagonism in most irrigation water is this one down here that's called bicarbonate. And bicarbonates, it is an anion that ties up cations in your soil, okay? And the cations in the soil, so all of us know CEC, we refer to that in our soil sample. What's your CEC in your soil? That's cation exchange capacity. And so cations are calcium, magnesium, sodium, potassium, and ammonium, okay? So those four, and we buy those as inputs. In other words, we go to the elevator, we buy that potassium, and we put it out there, and we think, okay, I'm feeding my plant potassium. And as soon as we turn our irrigation switch on, and we have bicarbonates in our water, they tie up what we just applied, and they make it unavailable to the plant. And so understanding what happens in the chemistry world when those chemical reactions that happen when we start irrigating are super, super important. To put this in context, if you look here, this is a Ward water sample. There's a pounds per 9 inches of water. Okay, so if we apply 9 inches of irrigation water and we have a bicarbonate level of 410 ppm, we are going to tie up 820 pounds per acre of cation fertilizers. 820 pounds per acre of cation fertilizers are going to get bound up with our irrigation water if we apply 9 inches. Most water in the Midwest, Nebraska, Kansas, South Dakota, is somewhere between 200 and 500 part per million bicarbonates. So this 400 is well within the range of what we see on most of our customers' properties. So if you look at University of Nebraska or most any university, they say that bicarbonates become an issue at around 150 ppm. If I remember right, it's been a few months since I've looked at this data. On our customers, I think less than 10% of our customers have bicarbonate levels lower than 150 ppm. So it's a problem on probably 90% of the fields out there, and that includes wells, surface water. It really doesn't matter. It's a problem pretty much across the board. So bicarbonate's the number one thing we look at. The other one is sodium. Sodium is definitely a really bad salt that if it gets too high is going to cause a lot of problems. Both of these samples are pretty low. This one's quite a bit higher, but anytime we're under 50 to 75 ppm, we're usually not going to see issues with sodium. But just kind of want to give a high-level overview of what we're looking at when we look at a water sample. Number one thing we're looking at is electroconductivity. The second thing is the bicarbonate level, and kind of gives us a feeling for how good or bad this irrigation water is. So this just kind of goes into what we just talked about, the mineral additions. You can see this particular sample has a sodium of 111 part per million. So for every 9 inches of water, he's putting on 222 pounds of actual sodium on his field. That is a level that has the potential to cause problems. It's not going to cause problems in every scenario, but it has the potential. The other thing to note is that bicarbonates and sodium, if you have both of those, you have an even bigger problem. Like those two really are antagonisms that can really cause some headaches in a field. And so having more than one of these things can be even worse. Okay, here's another sample. We've got sodium at 300 ppm, 600 pounds per inch, bicarbonate at 600. We're offsetting 1,200 pounds of cations for every 9 inches of water we put out there. So this particular water is extremely bad. It's the worst one that I've shown you. Anytime we see this sodium over 100, we're going to have problems have problems with fertility in that field. There are things we can do, and we'll talk about that in a little bit, some things to offset this. How do you manage it? It is manageable, but the first thing we have to do is we have to measure it and understand what we're looking at and what that potential is going to do to our field. I mentioned earlier that the reason that NutriDrip became so focused on water quality is because it will plug up drip lines. Okay, so subsurface drip irrigation systems can become plugged up if we have the wrong minerals in the water. Iron and manganese cause these problems primarily, but iron and manganese with bicarbonates make it even worse. So those two are also really bad news when it comes to drip irrigation systems. Again, there's things we can do to treat it, but we just have to pay attention to it. Understanding why our water is what it is. I think that's one of the things as you think about the water cycle and how water moves. It comes in as rain or snow melt, soaks down through the aquifers, and it's picking up anything that's soaking as it soaks down through those aquifers or into the aquifers. It's picking up anything that's in that substrate or the saturated zone there that water's sitting in. So it picks up the properties of that subsoil, and then as we irrigate, we're bringing that back up to the surface, and we see that then in our water sample. So as we get into the solutions, okay, so when we start talking about solutions, the number one solution to fix bad water is acid, okay? So lowering the pH is the number one way that we're going to fix this problem. And this is a slide of the pH of rainfall, okay? So if we go back to 2005, I want you to pay attention to this red line. This is the best, most recent data we've been able to find. The pH of rainfall in 2005 was around a 4, okay? So every time it rained, it was acid rain. Everybody was screaming how bad it was for the environment, and it was. But it was resetting our problem that we had in our irrigation fields. Every time it rained, it was kind of like hitting the reset button. Look at what the pH is. Here, this slide here is a 2020. We were up to 5.5. I would encourage you to catch the rainfall next time it rains and check your pH of your rain. We've done that on our farm, and our pH is at about 6.5. So this scale is clear up here now, if we were to continue this graph, okay? So the reset button is no longer getting hit every time it rains. And so we as farmers have to figure out how are we going to manage poor quality water and fix this problem that our water is bringing into our fields. So kind of just a little side note of something to think about. Why is this a problem that hasn't been there 20 years ago? It's because it was getting fixed every time it rained. And now that no longer happens. Another side note on that, I think I have a slide later. One of the other ways to fix it is tillage. And so where we used to be heavy tillage, every time we would till, that would kind of reset things. Where we try to move into a strip till or a no-till situation, now those bicarbonates stay bound up in the soil and they're not being released. And so tillage is another. So if you take the combination of higher pH rainfall and less tillage being done, both of those things are going to contribute to this problem, and we're going to see it in our yield maps. Irrigation water is the largest input on farmland and can completely change the soil dynamics. So just think about that. When we think about how many pounds per acre we put on of all kinds of fertility, lime, gypsum, whatever we're putting out there, water is the number one input that we apply to a farm, and I'll get a little more about that here in a second. We could do a deep dive on the actual chemistry. My goal isn't to bore you with chemistry, but a couple terms that you may have heard and that are super important when it comes to water quality. So alkalinity is a term that we hear about with drinking water and household water. It is directly related. So the key components of alkalinity, the number one is bicarbonate. Okay, so it is the number one thing that contributes to alkalinity. So a big part of alkalinity is bicarbonates. What about the pH? The pH of most irrigation water is well over 7, typically up around 8, 7.5 to 8. And so if we year after year are applying pH water of 7.5 or 8, what's our soil pH going to do? It's going to slowly climb. And so a lot of times we see areas that are heavy irrigation. So the farther west we go, the higher the soil pH is. And a lot of that has to do with the pH of that irrigation water that is just constantly contributing to the minerals in that soil. So pH is a big thing we want to look at and pay attention to. Water hardness. So hardness is somewhat related to this because hardness is the measurement of the calcium and the magnesium in the water. And calcium and magnesium are both minerals that our plants need, but the calcium in the water is not necessarily plant available. Okay, so it actually is when you have the calcium carbonate is the form that comes in through the water. It's calcium carbonate. That is not plant available. So we have to break this bond with some kind of an acid in order to make this plant available. So just know that even though you look at your water sample and says, well, I have calcium in it, that may or may not be a good thing. Matter of fact, most of the time it's a bad thing because it's actually causing some imbalances. Electroconductivity, we touched on this before, but electroconductivity is a look at all of the salts that are in that water. It's a consumptive or a summation of all of the different salts that are in there. And so it gives us a look at how many cations and anions are in that water. And electroconductivity is a super important measurement for how rich or how strong that water is. Total dissolved solids is kind of another, it's similar to electroconductivity. Those two are directly related. But a lot of times some people will talk about TDS or total dissolved solids. Those are both kind of interchangeable terms that are important to know and to understand. So if you haven't sampled your irrigation water, that's where I would start. Just pull a simple water sample, $60, $70 to get it analyzed at a lab. We can help with interpretation of those. What does it mean? How do you fix it? And how do you address the problem? And is it a problem? A lot of fields, I shouldn't say a lot of fields, less than 10% of the fields, I think it's not a problem. 90% of the fields, I think it definitely is a problem based on what we've seen. So to kind of add some context to the idea that irrigation water is the largest input on your farm. Okay, look at these numbers. 1 acre foot of water, 325,000 gallons. Each gallon weighs 8.3 pounds. We're putting out 2.7 million pounds of water per acre foot. Now I know not everybody irrigates an acre foot, so if you put out 6 inches, divide that number in half. This particular slide was put together by an irrigation consultant in Idaho, where they use 24 inches of water a year. So he's putting out 8 million pounds, or excuse me, 5.5 million with 2 acre feet, and 8.5 million pounds with 3 acre feet. So just to think about your irrigation method and how much water you put out, those are some massive inputs that we're putting out. And when you start calculating, you look at that number that we looked at earlier. Let's just bounce back here. And we look at these ppms. So again, if we look at this 111 ppm and you calculate that by the number of pounds of water we put out, this is the actual poundage of that particular mineral that goes out on every single acre for every 9 inches of water you apply. So the labs have already done that math for you. So you can obviously divide this by 9 and get your number per acre inch. But I would encourage you to really pay attention to what these numbers say. Again, when I mentioned earlier that calcium can be a good mineral, the problem is it's in the wrong form. So that 244 pounds is probably not going to be plant available without some amendments. Into a little deeper of every soil reacts to water differently. Okay, so we can draw this broad brush and say bad water is bad on soil, right? We could say that, we could make that comparison. But every soil reacts to the nutrients differently. If I have a sand, it's going to react completely different than a clay. Okay, so how do I measure what the reaction is when I irrigate? How is that actually impacting nutrient availability in the soil? So we're starting to use what's called a rapid soil test, or another name for it is saturation paste. Okay, so the common soil testing methods would be your ammonium acetate or the Haney. Those are very good tests. They tell us a lot of information, but I want you to think about a saturation paste a little bit differently, in the sense that it's showing us what happens when we irrigate. Okay, So if you think about the way an ammonium acetate extraction is done, they take your soil and they react it with a strong acid, okay, pretty strong acid. And then they extract some nutrients and they measure what breaks loose from the soil when you put that acid with it. And what we've learned is that that's not really representative of what happens on an irrigated farm. That may be representative of a dry land farm, but not on irrigation. And so I'll kind of dive into that a little bit. This is the process for ammonium acetate and malic, process for Haney. Haney's a great test. Believe a lot in that. You know, looking at water extractable organic carbon, there's a lot of really good numbers that we can learn from a Haney soil test or an H3A. But it's not, as I'll show you here in a second, it's maybe not the best metric for an irrigated farmer. So, what does a rapid soil test tell us? It basically what they do is they take 5 parts of water, 1 part of soil. They mix those together and they put it in a vacuum for 24 hours. They don't use any acid, okay? They just use, we actually send your irrigation water and your soil to the lab, and then they vacuum the water out of the soil, okay? So it is the readily available water that the plant can easily get out of the soil, okay? When you compare that with the acid extractions, those are extractions that show us what should be available to the plant maybe over a whole growing season. But if I'm an intense manager and I want to be able to know what is my irrigation water actually doing in that soil, I need to understand what's in that readily available plant water. So that's what the rapid soil test does. Is it shows us what's available in that readily available water. It looks very similar to a regular soil test. So this is an actual rapid soil test. You get all your micronutrients. You get ammonia and nitrate, electroconductivity, pH. So a lot of good metrics there, and we'll dive into that a little bit more here in a second. What we really want to focus on though is this cation anion balance. Okay, and so what we're doing here is we're pulling out which nutrients are anions, which ones are cations. The most dominant one of those is the one the plant's going to take the most in. Okay, I always thought growing up as a kid and working on the farm that if a plant needed potassium, it was going to go get potassium. That's not actually how it works. If the plant needs potassium, it is going to pull in a cation balanced with an anion, and then it's going to partition that in the sap or in the flow of the plant. It can't go out and choose potassium because it's hungry for potassium. So our job as a farmer is to balance this ratio. If I look at my cation balance and I've got calcium at 96, potassium at 11, magnesium and sodium, if my sodium is higher than my potassium, I've got a problem. And I will tell you this is very common in irrigation country, especially if we have a little bit of sodium in the water. This sodium becomes dominant and it pushes the potassium away and the plant cannot get a hold of the potassium. So these two are ones that we pay particular attention to. And if my potassium, the other thing we do is we rank them, and I'll show a couple slides in a little bit. So basically, if we were to rank these, calcium would rank number 1, magnesium number 2, sodium number 3, potassium number 4. Out of those nutrients, which one is the most important? Probably calcium's number 1, potassium's number 2, but it's ranked number 4. So am I going to be super efficient with my nutrient inputs if I don't address this problem? Absolutely not. I've got to address the fact that my potassium is the 4th ranking nutrient. What about on the anion side? We've got chloride, sulfur, and phosphorus. Chloride number 1 by a long ways, big margin. Sulfur number 2, phosphorus almost non-existent. Okay? That's a problem. Phosphorus needs to be at a minimum of 15 ppm. And almost on every test that we look at, as soon as we turn the irrigation system on, the phosphorus drops from, let's say we start at 20 ppm, it drops to less than 5. In other words, our water has so many antagonisms in it that it's blowing the phosphorus out of proportion and the plant can't get a hold of it. Okay, so here's a chart that shows the difference between different extraction methods. Okay, so this blue line here is our malic. We've got ammonium acetate extraction, H3A, and then finally the rapid soil test or saturated paste. Okay, so here's our Malic 3. We've got potassium numbers in the hundreds. These are 7 different zones on a particular field. So this grower zone sampled this field, and so basically we're looking at all the different zones here. So you can see his potassium levels, if he's looking at a standard soil test, are going to show that he's got really good potassium levels, right? Nothing to be worried about here. H3A, or a Haney test, it's showing that, yeah, maybe we've got some problems. Now we turn the irrigation system on, and we look at it from a saturated paste. We've got some massive problems going on over here in a couple of the zones, okay? So what we've learned from doing this testing is basically where we thought we had enough nutrients available, our water is making those nutrients unavailable through the antagonisms that are in that water. Okay, here's another way to look at it, and this is a good example here. Apologize, it's cut off, but basically this is a deionized sample. So let me explain what that means. On this rapid soil test, when we send this into the lab, we take your soil and your water. We send that into the lab. They run it 2 different tests. They run what's called a deionized. So what that means is they take RO water, or water that has nothing in it, has an EC of 0, okay? And they do that same saturated paste test, and then they show you which nutrients are available under that scenario, okay? I like to look at this and say, this is what happens when it rains. These are the nutrients that are available when I have rainfall coming out of the sky that has an EC of basically 0. As soon as I turn my irrigation system on, so this is my irrigation sample, now this is what's available to that plant. Okay, so let's look at the things that changed here. So under the rainfall scenario, or the deionized sample, we've got chloride as number 1, nitrate is number 2, sulfur number 3, phosphorus number 4. Turn my irrigation system on, sulfur goes through the roof, right? Which is common. A lot of wells are high in sulfur. Okay, that's not uncommon to see that. Number 2, now we have chloride at number 2, nitrate at number 3. Phosphorus was already low, but it got cut in half. So we went from bad to worse. We turned our irrigation on. Okay, not a great scenario for high efficiency or high return on investment here when it comes to fertigation. Now let's look at what happens. So one of the other things we can do is we can send to the lab what our fertigation recipe is. Okay, so basically here we have the well water. So this is the irrigation scenario. This is my fertigation recipe. This is what I'm going to do when I fertigate. So now I can actually see when I fertigate. Okay, here my chloride with my well is number 1, sulfur number 2, phosphorus number 3. Look what happens to my phosphorus load when I turn my fertigation pump on. Okay, it jumps up to number 2. We're well above 15. Sulfur doubles, but it's number 3. This is a much better ratio. We like this pie to be evenly divided. Okay, we actually need chloride. A lot of times I used to think, well, chloride's, that's a negative salt. That's what I use to melt the ice on my sidewalk. I don't know that I necessarily want on my plant. I actually do. The plant needs chloride, so it's not that this is a huge problem, but it can't be so dominant, right? Look at the percentage of the pie that chloride makes up here, and these are the other 2 nutrients that we really need. We need that sulfur and that phosphorus in our system. So it helps us to understand what is the water doing to nutrient availability, and then what is my fertigation doing when I turn my fertigation system on. Here's another lab analysis. This is on the on the cation side of a well out by Lexington, Nebraska that we did this spring. So here it is with this deionized. You can see his magnesium's pretty high, potassium's really high, right? You get out in that Holdridge, Lexington area, they got super high potassium levels in the soil. So that's not surprising to see that. They also have high pH, and that pH is high because of potassium, not because of calcium. Where I'm from, our pH goes up and down based on calcium. As you move west, the pH moves because of potassium. So here we turn our irrigation system on. This well, I don't think I have the water sample for this particular well. If I remember right, it was around 100 part per million sodium. Look what happens to sodium. It goes from a 37 to a 113. It goes ranked from number 4 to number 1. That's a problem, okay? And then what happens to all my other nutrients? Potassium gets cut by a third. Magnesium gets cut by a third. Calcium goes up just a little bit. So again, not an ideal scenario if this isn't addressed. This particular grower has not had success with fertigation, right? They've shut all their fertigation pumps off. Well, now I think we understand why, right? Because fertigation doesn't work in this scenario because there's too many antagonisms in the water. So if what happens if we fix those antagonisms and start fixing this water and make it where it's balanced and that plant is happy again. Okay, so how do we measure this? How do we manage fertility? We're looking at the relationships between cations and anions. All negatively charged elements will compete for uptake, and all positive charged elements will compete for uptake. This is a super important concept that I did not understand. I always thought that plant, when it needed nitrate, was going to go get nitrate. That's not how it works. It has to compete with the other anions and cations that are in that soil and in that system. Okay, back to kind of a little bit of the water sample. There's different ratings that we can give that kind of show, hey, is this one going to be a problem? Which ones are significant problems? But a lot of really good metrics in here. One of the take-home quotes, though, that I want you to remember: what your water is, your soil will become. Okay, what your water is, your soil will become. Especially if you're in an area where you irrigate more than 4 to 6 inches a year. Now, I know as you move farther east, we don't irrigate that much. I'm in northeast Kansas. We probably average 4 inches of irrigation a year. We get 8 inches of rain. So our system flushes pretty well. But as you move west and that rainfall goes down, irrigation amount goes up, this is a super important concept that needs to be addressed. Okay, gonna go into kind of the next step of measuring. So we've measured what's in the water. We've measured how the water is reacting with the soil. Now what about the plant? Okay, there's a whole nother step of, okay, I understand what's in my plant, understand what's in my water, what's in my soil. What about the plant? In the past, we've been big proponents of tissue sampling, and tissue sampling is a great method for measuring what has happened, okay? What its weakness is understanding what's happening today. Okay, this morning my wife and I came up here to Lincoln. We went to Quest Labs and we had blood work drawn. I want to know what my cholesterol is. I want to know what's happening in my body today. If I wanted to know what has happened to my body over the last 12 months, I would take a hair sample. They would take my fingernail and they would process what has accumulated in my tissue. That's what a tissue sample is. It's an accumulation of what has happened in your field. A sap sample is a measurement of the xylem and the phloem. It's the blood of the plant. So if I'm an irrigation and fertigation person and I want to manage that plant to the highest level possible, I need to know how are my changes impacting the blood of that plant. What's going on in that xylem and phloem that I'm impacting it either in a good or a bad way. So we've done thousands of tissue samples in the past. It's a great method, but you have to understand what its weakness is. And sap sampling is a whole nother step that gives us real-time information of what's going on in that plant. So understanding the differences is super important. We have this on our website. We've posted this, kind of showing the differences between the two, where to use them, where to use a sap versus where to use a tissue. The sap sample is collected similar to a tissue sample. You take the biggest difference is we take new tissue versus old tissue and we compare those. Okay, because the plant uses its old tissue as a reservoir. And we know that because as the corn plant gets late in the season and we start running out of things, what happens? These bottom leaves start to drop, they turn yellow. We can predict that with a sap sample because we can see that the flow of those nutrients, the mobile nutrients, there's mobile and immobile, but if we watch the mobile nutrients, we'll see these nutrient levels in this lower leaf crash. And about 2 weeks later, those leaves are going to start senescing, because we've mined all the nutrients out and the plant moves it up in the plant and puts it in that ear. So if we can start measuring that, we can get ahead of the curve and start to understand what's going to happen in our field versus waiting for a tissue sample, which tells us, it's like looking in the rearview mirror saying, well, here's what did happen. I want to know what's going to happen. So that's where we feel like sap sampling has given us a new look on what's going on. This is a sap sample. I'm not going to dive into this real deep, but a couple key points I want you to remember. We have the anions and the cations, just like we did in that soil sample, in that rapid test. And the ranking of the anions and cations in a sap test will almost always match the ranking on the sap test. Okay? So in other words, those readily available nutrients that are in that water, that are easy for that plant to get, will show up in the same order that they did on my soil test. For those of you that have done tissue sampling, it's almost impossible to correlate a soil test with a tissue test, right? I can have super high potassium in a soil test, and it will almost never show up on a tissue test. Those two are hard to correlate. On a SAP and a RAPID, we can actually start to get some correlation. And so we feel like this is a tool that gives us a lot better look at what's happening in that plant system as those roots are bringing things up out of the soil. One of the books I read that kind of changed my thinking about this, it's called Ask the Plant by Charles Waters. One of the things he said in there is we're only about 10% efficient with phosphorus, okay? 10%, think about that. We're spending, what's phosphorus, how many dollars a ton today? And if we're only getting 10 cents out of every dollar that we're spending with our traditional ways of applying phosphorus. So this is one of the things that we're focused on, is how do we raise this efficiency even to 50%? If we went from 10% to 50%, that would be massive. And so as we think about how do we fix these problems, that's one of the ways we're doing this. Okay, a couple key takeaways. Why have we gotten mixed responses from different fertigation applications? If I go to a farmer and I give him a fertigation recommendation and it works over here and it doesn't work over here, why? Those are questions we've tried to figure out. And now we're starting to understand that a lot of it has to do with what's happening in the water and then how that water is reacting with the soil. If irrigation water is our largest input, we need to account for what it's doing in that soil. It is changing the soil dynamics. It's changing the chemistry, it's changing the structure, it's changing the amount of oxygen in that soil, and it's super, super important we pay attention to that. Plants cannot select between different anions and cations. Deionized water is equal to rainwater. So again, that's one of the things that's been eye-opening for me, is to understand that my plant experiences one thing when it rains, and it experiences something completely different when I turn my water on. And then it's something different when I fertigate. So how does the plant make up for all of those differences? Oops, wrong button. Phosphorus is your battery. Okay, this has been kind of a new, I've always known phosphorus was important, but understanding how important phosphorus is. It drives every plant function inside that plant. And so we have to understand where our phosphorus levels are, and they're super, super important. I didn't mention this earlier, but Calibrated Agronomy is the partners that we've partnered with on a lot of this. And so basically NutriDrip is a partner with Calibrated, so that's kind of the mesh there. Just a few key points here. I'm not going to dive too deep into these slides. These are some data from a year ago in Nebraska here. The take-home message here is that it's not economical to treat our water all the time. Okay? In an ideal world, we would lower the pH of the water with phosphoric acid. That's the number one solution that we found, because phosphorus is the thing we're the least efficient with. It's the thing that is least available to the plant, and it is deficient most of the time. So if the fix is lowering pH and raising phosphoric acid seems to be the number one solution that we've come up with. The problem is that in order to do this all the time, I'm going to spend $1.44 per minute that I pump with 800 gallons a minute on this particular scenario. So if I were to do that, it's going to cost me $586 an acre inch to fix that water all through the season, right? We can't do that. It's not going to work. But what we are finding is that if we treat it, let's say I've allocated $50 an acre for phosphorus. If I take that allocation from my dry band or dry spread and I put $50 towards a phosphoric acid, my efficiency goes from 10% to 50%, and that's where we feel like that's the low-hanging fruit. That's where we feel like this does make sense and it is cost-effective to do. Some of the other things we're looking at are sulfur burners. We've been working with sulfur burners for a number of years. Basically, a sulfur burner takes dry prills and then it burns it, and it injects the sulfurous gas into the water, lowers the pH, brings plant available sulfur into the water. Sulfuric acid is another solution. So there's a number of different products that we work with that kind of help us get to this. There's the economic versus the agronomic, right? The agronomic solution is we should treat it all. It's not economical, so we've got to find that happy ground in between there, where we have an economical return. This is an example of a test where here's the untreated irrigation water. You can see its phosphorus and potassium levels super low, almost no phosphorus, potassium at 20 ppm. Introduces the phosphoric acid. We get phosphorus up to 22 and potassium up to 35. So kind of just an example of what a treatment looks like. So these are some of the different acids, different products that we're working with. There's a lot of different things we're using to get that accomplished. I think I'm running short on time, so let me just check time here real quick. So just kind of wrapping this up. NutriDrip's doing a lot of different things with moisture probes, satellite imagery. One of our current new things is manure. So we're a company now that we separate manure, separate liquids from solids, and then what do we do with the liquid portion of that? Not going to spend much time on this, but basically one of the things we're doing is we're taking liquid manure and using it as a fertilizer. How do we take manure, put it on your planter, use it as starter, use it as a foliar? So some things that we'll have some data on here in a few more days. So with that, I'll take questions, and I want to thank everybody for coming. So, any questions? Kyle, I know you got something.
Yeah, it'll take way too long.
What should we be drinking? Water.
What should we be drinking? That's a really good question. So the answer is not water with a 0 EC. Okay? And that's actually, distilled water is actually too clean. Yeah. And if you go to California where they get a lot of snow melt, they actually have to add gypsum to their irrigation water, because if they don't, it strips the soil of all the nutrients. It's so clean that it will cause negative impacts because it's too clean. Same thing with our drinking water. Our drinking water needs to have some minerals in it to be ideal. So distilled is actually not right. It would be something with an EC of probably 0.2 to 0.5, but it depends on what salts are in there. And I'm not a health expert, but I can tell you it's not distilled. Yep. Any other questions? All right. Thanks for your Alan.
I would just make a statement. It makes sense, what you showed us up there in terms of how the water changes nutrition availability. It's really hard for a farmer to just take a good sample test, put your prescription out there and run it, and think that that's what you're going to have.
Right.
What would you recommend a guy do in that to start getting that whole system right?
Yeah. So the question is, how do we? What's practical from a testing standpoint? Is a grid sample going to work once a year, once every 3 years? So our answer to that is no. We don't think that's a good idea. We like the idea of zone testing. So take your irrigation map. What's irrigated? Look at the yield map. Pick out 2 or 3 zones: high yielding, low yielding, maybe a medium yielding zone, and go do rapid soil tests in all of those zones. And what you're going to find, I made the comment earlier that sands, silts, and clays all react differently, right? That cation exchange capacity is huge when you look at that interaction. And so as we have varying CECs across that soil, we have varying pHs, those reactions are going to be different in every one of those zones. And so understanding what can we impact. One thing I would say though is that phosphorus has showed up 99% of the time as a problem. Okay, phosphorus is an issue everywhere. Like I'm just trying to think if there was 1 or 2 samples that came back with adequate phosphorus levels, and they were fields that had long-term manure